In this first episode of our Quantum on the Back of an Envelope series, we'll take a look at singularities that may spontaneously appear in the time evolution of Schrödinger wave functions. Consider a free quantum particle described by a spacetime dependent wave function. For simplicity, let's adopt the so-called atomic units in which the Planck constant and the particle's mass are both equal to 1. Then the Schrödinger equation takes this form. The free particle Schrödinger equation has the following explicit general solution. Given an initial wave function psi at time 0, the wave function at any later time t can be expressed as the following integral. This is a standard textbook result that can be used to propagate any initial probability density of the particle in time. It might not be very well known, however, that this propagation does not necessarily preserve the smoothness of the wave function. That is, an initially continuous and differentiable wave function may, all of a sudden, develop singularities. Here is a neat example of a spontaneous singularity taken from a brilliant book by Asher Paris, entitled Quantum Theory, Concepts and Methods. Consider the following initial wave function. It is normalizable and everywhere continuous and differentiable. We'll ignore the normalization constant, as it's irrelevant to our discussion. To find the wave function at a later time t equals 1, we can use our propagation integral, which yields the following expression. This integral can be evaluated explicitly in terms of a modified Bessel function of the third kind, but we won't go into that here. We'll simply point out that this wave function is no longer smooth everywhere. It exhibits a singularity at the origin. Indeed, at x equals 0, the wave function is given by this integral. The integrand has slow tails. It decays as 1 over y to the power of 2/3 as y tends to infinity. This decay is not fast enough for the integral to converge, meaning that the value of the particle's probability density at x equals 0 is infinite. Here is a sketch of the time evolution of the corresponding probability density. While the initial probability density is smooth everywhere, it develops a singularity at a later time. We hope you enjoyed this episode of Quantum on the Back of an Envelope. To learn more about what we do, please visit us at our website.